Oh, thank you very much. Thank you very much, Irene, for your great introduction. And it's a pleasure to be here and also to meet also if online all of you. And today I will try to present something that probably had some ideas of what you already have seen in these days related to the structural retrofitting. And let me close something, sure, okay. And the idea I had in mind is to present some of the results we performed in Politecnico di Milano in the last year with the idea to reimagining reinforced concrete for structural retrofitting. So the most important aspect is to understand what is structural retrofitting, and for me is the modification of an existing structure to improve its performance and typically to make it more resistant to loads as, for example, earthquakes or others. And I will try to go deeply inside to this topic, trying to do an analogies between human and RC structures. And then I will present you the results of our research in terms of some innovative solution. At the end, I will do some conclusion for you. For human, for example, you know probably you may suffer muscle or skeleton pains, joint pains for your knees, spine, some postural deformities, deterioration with age in particular. And RC structure practically works in the same way, so we can do some analogies. And we may have overloads on members related to maybe new standards or the change in use, connection damage, permanent deformation, or other deterioration as cracks, corrosion, and etc. And it's very interesting to understand that we can prevent or fix the human body, prevent the pain, maybe going to the gym, and then you can fix if you have some problems. And for the structure, it's very similar. So you maybe just already know that there's strengthening or retrofitting techniques that works before or after damages. As for example, I showed you some example, for example, jacketing with RC or steel plates, external post-tensioning, or other new innovative material as FRP or FRCM, which works mainly on RC structure on the external surfaces. But the question is there any alternative with respect to prevention or fixing some damages, so to strength or retrofit? In my opinion, one of the possible alternatives is to make the backpack lighter. So you may work on the mass reduction in order to have a structural reinforcing technique. And what is important to understand now is which are the loads, which are the weight you have in the structure backpack. And so if you think about reinforced concrete structure, they are very massive. And so you need to think about this list of loads reparted in a different portion. You have, for example, external loads, which are named live loads, people, snow, wind, similar. And then you have both permanent non-structural load as pavement, systems, partitions, or facade element, roof element, floor, etc., up to arriving to the skeleton, to the part which is the most important in terms of structural behavior. But it's important to notice that, for example, the horizontal elements as floor or slabs and roof as a significant portion of the total weight of the structure. And this is the point in which I want to underline my presentation in order to show you some example of alternative solution which can be included in terms of retrofitting. To do this and to understand which are the main advantages you may have, I start doing some very simple analysis, linear response spectrum analysis. And I included different parameters related to the grid shape, the grid size, the number of floor, and the different use of the building. And I tried to stay between the typical on the left, 7.5 and 2.8 kilonewton meter square for the weight of floor and roof, up to arriving to the lightest one. So clearly the reality stay in between the two, because clearly if you make something which is very, very light, you may lose something in performance. So I will propose you three alternatives which stay above the less than 50% in terms of weight, the typical and traditional solution, 2 cases for floor element and 1 for roof element. In terms of results, after performing this analysis, on the left side, you can see that a reduction of the loads clearly
led to a variation of the section of the structural element. But clearly, if you think about structural retrofitting, you cannot remove portion of the columns, for example. So it is not these the results we wanted to search and wanted to understand for speaking about the effect of mass reduction. But we may think that clearly maintaining the same dimension of the column, of the beam, of the structural elements, we may have clearly less stresses. So due to this, the lower action we have are related to the mass reduction. On the right side, I may show you also other important aspects related to, for example, the reduction of the bending moment in the joint at the foundation level when you reduce the masses. This is quite typical, especially in case of seismic action. So starting with these two possible effects, it's immediately it's immediate to think that you may have solution which can change structural masses in order to have a reduction of the action on the structure itself without changing the geometry of the structural element. So I will now show you some example of our research, and in particular, I will start with this, which is the result of a private research project conducted by Politecnico di Milano together with a company of which stay in Milan. And the idea behind this was to realize a slab, which is a partially prefabricated slab made with innovative material. And the goal of this research was to arrive to the experimental validation of this solution, in which the structural efficiency and performance are related to the use of new materials. I will show you them. I will show you later when I'm speaking on. And then to improve the construction speed and make the solution lighter. On the bottom right side, you can see that the distance between the beam and the solution I'm presenting, it's very similar to the ribbed slab with hollow clay blocks, and has a distance between the beams which stay close to 1 meter. So this means that you have 2 times distance between the beam, using less material, and so in a sense to lower material consumption in the view of sustainability. This slab is realized with beams, and as I told you, with 1 meter distance between them. And then these disposable formwork, I will speak about them later, which are very thin. And then at the end, but only at the end, you will have some procedure to cast in place material as FRC. Here, I want to show you the results of the beam elements. They were realized with very high performance fiber reinforced concrete. The idea behind this was to reduce the section using concrete, which has a capacity which stay at 120 megapascal in compression, and adding steel fibers in high dosage in order to have a behavior which is hardening after the formation of the crack in tension. And this means that you may improve the performance, but especially reduce both steel bars quantity in terms of longitudinal bar, but especially in the stirrups one. And then you can also reduce the material consumption. And this means that also if the material itself has a global warming potential, which is higher with respect to the typical reinforced concrete, you may use very less quantity and have, in general, a reduction of those parameters, making the solution sustainable. We have done the test to prototype the solution, to test them, and we experimentally validate this kind of beam. And then we pass to the TRC shells. They are realized with textile reinforced concrete, so micro aggregates in order to don't have to have very thin elements, which ranging between 6 and 9 millimeters of thickness in the different position. And it was very interesting to use material like this because you have the chance to remove completely the steel bar within this very thin shell, including an air glass fabric that works in tension where the material, where the concrete cracks. After a shape optimization you are seeing in the middle, we arrive at a solution that we tested both in centered load and edge load, due to the fact that this material, these elements, has to work in a condition in which the operators walk under the floor before the casting of the top surface FRC. And due to this reason, we needed to understand, and you can see it on the equivalent footprint on the right side by 100 times 100 millimeter square, you may see that the material has very high response in terms of formation of cracks up to the arriving of the fabric rupture. Moreover, it is important to say that thanks to the very thin shell, these elements are very, very, very light, 30 kilograms each one, which is around 1 meter times 1 meter in plan. And this means that two operators can move them very easily, increasing the making the process very rapid. So after that, I want to propose you another important solution, which is the results of a project of Regione Lombardia related to industrial buildings. And the idea behind this project was the fact that it could be interesting to introduce new roofing panel in order to have a lighter solution over around 1.2 kilonewton meter square, improving the structural safety and durability thanks to the use of new material, very similar to the one I showed you before, and include also thermal efficiency thanks to the sandwich shape of these elements, including inside an APS layer, and also including with the U shape, I will show you later, the compatibility with photovoltaic devices. In this way, we may obtain something which is not only structural retrofitting, because to the fact we have a reduction of masses, but we also obtain something more in terms of energy, in terms of thermal efficiency and production of energy. So this is the section of the elements. And on the top side, we have an entire crust of HPFRC, which is very similar to the very high performance fiber reinforced concrete I showed you before, and a very thin layer on the bottom side in TRC. I already mentioned that thanks to the TRC, we can work with very, very thin material, very, very, very thin members. After the optimization of the material in order to arrive to the production of the specimen, we did something also in between. So some tests on small sandwich panels, because also the EPS inside, which is intended in the sense of insulation of thermal dissipation, it's also a very important element in terms of structural behavior, because it has to connect the top and bottom faces and to guarantee the complete connection between them. So we had to test him before arriving to the prototyping you are seeing on the right side. After that, as before, we arrived to experimental validation and we performed a list of tests. So the panels are 5 meters long, as you can see on the left side, they are very big, they were very big. And we decided to also test those specimens in order to be used in industrial buildings, also under fire. So on the right side, you can see an example and the scheme of a test under fire, and also the last part of the test. But we had the chance to verify that the minimum requirement, which is 30 minutes after the starting of the fire, are satisfied. After that, we had the chance, after the closing of the project, to place and to dispose 3 of these panels in close to the campus, in the campus of Lecco, and also to add 3 photovoltaic devices. And we had the chance to monitor them in order to understand, and you can observe the different line on the left, bottom left, and you can observe the different variation day per day, thanks to the fact that there was sun, so day and night. And after these 7 years of exposure in this unsheltered environment, we had the need to remove this panel from the campus, and we decided to repeat the same mechanical characterization on the H panel we had at the beginning. And on the figure I'm showing you, the red curve is the aged panel, the gray and black are the previous one, the time 0 ones. You may see that there are some variation in terms of behavior, but no variation in terms of maximum capacity. And there's an increase in crack controls thanks to the fact that this innovation material has to be in their complete entire life a continuous effect of hydration, and they increase their performance. Moreover, in order to be sure that the unique two reinforcing steel bar we had in this panel doesn't have any problem of deterioration, we check them by monitoring both the corrosion potential and then doing carbonation. On the right side, you can see a portion of the bar, which is completely clean after the 7 years of exposure, and making the solution also durable as we intended them at the beginning. And the last example I wanted to show you is more recent. It's from 1 year ago, and it's a modular, lightweight, and eco-friendly shallow beams. And this was realized within the Meta Building EU innovation project, together with two companies, the Thesis from Salerno and Refer from Switzerland. And the idea behind this was to use material which come from the construction of previous buildings in order to have recycled aggregates, and also to use in terms of to connect the different modulus of this beam, to use bars which are shape memory alloy material in order to have the chance to use them in different life cycles, to remove the shallow beams, to have the chance to recreate the shallow beams again, in order to make it more usable. Moreover, this bar, thanks to their capacity to be to have a memory of their preliminary shape, they can be a solution for post-tensioning. So they are not working only to compact together, to make together all the different modules you see on the top left, but also to add a post-tensioning, similarly to what you have in post-tension reinforced concrete. So the main characteristic of this solution should be sustainability, innovation, thanks to the use of new materials, and the reduction of environmental impact, thanks to the fact that we reuse waste from the previous building, and the reusability in time. The RAC, recycled aggregate concrete, was developed starting from a solution which was 55 megapascal of resistance in compression, and comes from a patent from the Thesis company. And thanks to this preliminary analysis of this material, we arrived to average strength which stay at 54 megapascal, which is perfectly in line to what we had in mind. On the right side, you are seeing the shape memory alloy bars, which are produced by Refer. And I'm trying to, with the graph, to explain you how they works. The gray line represents the pre-deformation in the production plant. So the materials start to have a new shape, which is longer than it was at the beginning. After that, when you use them in the construction, you may have the activation phase, in which by heating and cooling, you have elongation of the bar, and then it comes back to the original shape. So it will be shorter than the dimension you have when you place it in the structure, and then you can use it in service condition. But it will be really more clear in the next slide, because we arrived to the rack modulus production in a company, which is Magnetti Building, close to Lecco. And then we have the assemble of the different modulus, placing the bar inside, connecting with one to each other, the different modulus. And then we also applied some thermocouples to have the chance to control the temperature we arrived to. And then there's the prototype, the post-tensioning phases. So in the first phase, and you can see on the right graph, top right graph, you see the phases of temperature variation. We introduce a current on the bars in order to increase the temperature up to 360 degrees. And in this phase, there's an elongation of the bar. So the different modulus in this phase are not connected one to each other. So they are free to move. But then in the cooling phase, the dimension, there's a shape shortening of the shape memory bars, and these make the post-tensioning effect. And on the bottom graph in the middle, you can see a blue line which represents the equivalent strain measured on the external surface on the element. making us sure to have realized the correct post-tensioning we had in mind in the preliminary design. So as before, we have done mechanical testing on the left side, but we also had some preliminary design abacus due to the fact that this solution is very particular because to the modularity. So you have the chance to create different modulus in terms of shape, length, and also eventually introducing some insulating layer if needed. And so we try to have a preliminary design abacus to obtain a solution which is usable for typical floor and in the weight I'm speaking at the beginning. Then we pass to the evaluation of environmental performance, because clearly we are using aggregates from previous concrete material to previous concrete buildings. And so we are sure that we are reusing the solution. But with respect to the ordinary solution, we risk to have an increase, as you can see on the second column, of the single score that represents in a certain way the global warming potential of the solution. But the most important aspect related to this kind of element is the fact that you can reuse them more than one time, especially regarding the bar with shape memory alloy, because doing the same process as before, so pre-deformation, heating and cooling, you can remove them and introduce again the post-tensioning in another solution. So in scenarios in which you have 50% or 100% of reuse of those materials, you may see that there's an extension of service life, but also a very, very, very reduction of global warming potential, make this solution eco-friendly. So mass reduction may be a structural retrofitting technique. As for humans, it could be also for structures, and due to the fact that you have lower action, and it could be an alternative, or it will be used in parallel with strengthening or retrofitting. But it is more important in the case in which you have to preserve the architectural significance of the element without modifying shapes of the skeleton or functionality. Maybe you can only change what is maybe less significant in terms of architecture, which is maybe the floor, and then you can reduce the loads. So how you can do it? I think you can reimage reinforced concrete in order to obtain innovative solution, which is lighter, eco-friendly, sustainable, modular, and so on. And this could be done only doing research and using new material as the high-performance material I showed you, using shape optimization in order to have something which is performance, which has performance, but it's also less invasive on the structures. So I'm at the end of my presentation, but I hope to be, I'm happy to have eventual questions and so on. So thank you very much.